Okay, let's conclude this story on numerical instabilities and stability criteria. So in the unstable case, we looked at the solution basically for the quadratic equation. Whoops, went too far back. The quadratic equation here, we were seeking the solutions, and we said it has two solutions, obviously, depending on sigma. One is a stable case where we have real solutions. The other one is the unstable case. So if magnitude of sigma is greater than 1, then this becomes imaginary. So b delta t equal minus I sigma plus minus square root 1 minus sigma squared was the equation. So b delta t in this case is minus I plus times sigma plus minus s, where s is reverse signed, sigma squared minus 1, which is greater than 0 because of this. So for sigma greater than 1, we have sigma plus s greater than 1, and hence b delta t to the n goes to infinity as time step n goes to infinity, which means the numerical integration as it proceeds in time begins to have a growing solution which becomes too large. As I said, going from 19 degrees centigrade today to 100 degrees centigrade tomorrow, and maybe unrealistic 200 degrees centigrade on the third day, and so on, can result from unstable numerical methods. For sigma less than minus 1, we have sigma minus s less than minus 1. So we have, with s is still this expression here, and b delta t to the n diverges as well. Okay, so remember sigma. What is sigma? You remember? Sine alpha is our sigma. So this is the original sigma, u delta t dx sine k delta x. Basically, it's an indication of how fast the numerical signal is moving when we integrate forward. Okay, sorry for flipping back and forth, but basically, if magnitude of sigma is greater than 1, then the solution explodes, which is not what we want. So we looked at numerical solution that is stable but had error because of this numerical mode, and we are looking at a numerical solution for some choices of delta t and delta x where the solution blows up. So we don't want that either. So Cm n plus 1 is again our equation, Cm n minus 1 minus u delta t delta x, Cm plus 1 n minus Cm minus 1 n. So this is C plus u dc dx discretized. So the criterion then essentially for mod sigma being less than equal to 1 is that u delta t over delta x times sine k delta x has to be less than equal to 1. This is called the Courant Friedrichs Levy criterion. This paper was in fact published in 1928, way back when, almost 100 years ago. They realized that numerical solutions can have such instabilities, and some criterion is needed to suppress stabilities, which basically boils down to how fast you can integrate. Remember, we want multiple things. We want delta x to be as small as possible because we want to be able to, let's say, make weather forecasts at as fine a scale as possible in space. You cannot say 500 kilometer area will have a temperature of 19 degrees centigrade tomorrow when you make a forecast. You want to be at a scale that's reasonable, let's say of a few kilometers, and you want to be able to use delta t as large as possible because the computational cost has to be kept low. So this is what numerical integrations want to accomplish, and you want to have a stable solution but also accurate solution. So that's the overall goal of numerical integrations. So in this case, the magnitude of u delta t over delta x has to be less than equal 1 as delta t and delta x go to 0, because this would go to 1 as we said before. What does this mean physically? So think of it this way. We are dealing with a wave equation. So this is the space-time grid and area of influence of the CTCS scheme we used in 322, this one. So we're going from solving for m at n plus 1, but we need m plus 1 at n, m minus 1 at n, and we need m at n minus 1. That's how we integrate forward. So here is the how the domain of influence of the numerical method goes as we integrate forward. So if we are integrating here, we are looking for this and these two. So and then so on going back. So we are carrying information from time t equal to 0 from here to reach this point, essentially. Okay, how is that related to the physical process itself? So imagine that we have obviously dealing with a linear first order equation which we have analytical solution for. So the waveform is moving along what is called a characteristic, which is basically the constant phase line. Remember, x minus ut is the phase of the wave, e to the kx minus ut, right? So that line is the physical line on which we are trying to find the solution. So your domain of influence of the numerical method has to remain within that. If you take information from outside here or outside there, you're going to introduce false information into the solution, and you are going to end up with unstable solutions. Okay, so you can write this Cfl criterion. This is our Cfl criterion. We can write that as 1 over u greater than or equal to delta t or delta x, which is the same as u delta t or delta x less than or equal to 1. Basically that means you have to choose delta t and delta x such that you have to obey the speed at which the signal itself is propagating. Okay, and this is very important. That means when the signal, whatever it is you are looking for, let's say how fast pollution is moving, how fast a heat wave is moving, how fast a storm is moving, I'm just giving you examples. Then there are high speed propagation processes in the atmosphere. Ocean typically doesn't move as fast, but then the Cfl criterion still has to be satisfied because you have everything happening at a slower time scale. So that means you can either keep this smaller than 1 by increasing delta x, in which case your resolution is lost because you want to predict at as small a scale as possible, or you can reduce delta t to keep this small, in which case your integration is going to take a long time. Computational cost is going to be very high. So you know how the optimization has to be done. So essentially we have to move towards numerical methods that are as stable as possible, or they have to be stable, as accurate as possible, and resolve things at the spatial scales and temporal scales that you want, or the forecasts and solutions call for. Okay, so we can extend this to an example of the temperature equation. dt dt, temperature change, is given as kappa del square t del x squared. We will not say what this is. You can think of this as eddy diffusion, for example. So in this case the criterion would end up looking as kappa delta t or delta x squared is less than or equal to 1/2. So depending on the equation and the processes you are representing, the Cfl criterion will give you the constraint on the time step and the spatial resolution. Okay, that's the idea of numerical integration, numerical methods, numerical instabilities, and stability criteria, and how we can generate artificial growing errors, growing in space or in time, and we have to watch out for those. We will look at some methods next which are stable. but they have other issues. You can have a very stable solution but end up with errors in a different way. For example, when heat is moved, some of it may go into temperature, some of it may get dissipated, some of it may go into evaporation, and so on. And just because the method is stable doesn't mean that all these conservations will happen, all these compartments of distribution of energy into heat, evaporation, and so on will happen. So physics ultimately is still the constraint that numerical methods have to obey, because even if you produce a stable solution that produces very wrong solutions for temperature or evaporation or for heat and so on, then you haven't accomplished anything, even though you have a stable numerical solution. Okay.